Our last example will be an integral over a region T bounded by the planes x equals 0, y equals 0, z equals 4, and the surface z equals x squared plus y squared, and then lying in the quadrant where x and y are both greater than or equal to 0. So essentially, we want to find an integral that is in the first octant. Okay, it's going to be between the surface z equals x squared plus y squared. So I can kind of draw out z equals y squared as a parabola, and then z equals x squared as a parabola. Okay, going up to when z equals 4. And then that creates this kind of quarter of a bowl. And that quarter of a bowl goes from z equals x squared plus y squared all the way up to z equals 4. So essentially, the region in the xy plane is going to be given by x squared plus y squared is less than or equal to 4. So if I graph x squared plus y squared equal to 4, that's a circle, or quarter circle in this case, of radius 2. Okay, and we're going to integrate inside that quarter circle. Our goal is to integrate the function x dv. So I want to essentially form a triple integral. That triple integral is going to be of the function x, and then I'm going to integrate dz, dy, dx. So let's start with the limits of integration in z. Z starts at the bottom of the bowl, so that's going to be x squared plus y squared. And then it goes up to z equals 4. And then I'm going to describe the region in the xy plane. Okay, so I'm going to start where y equals 0. And then I'm going to go to y equals the square root of 4 minus x squared. And then finally, I'm going to integrate x from 0 to 2. So we're thinking about this as starting at the bottom of the bowl and then going up to z equals 4. That's in the z direction. In the y direction, we're going to start at y equals 0 and then go up to y equals the square root of 4 minus x squared. That's the boundary of that circle. And then we're going to go from x going from 0 to 2. So I'm going to note as I do this integral that that the dz dy parts of the integral don't depend on x, right? So I'm going to look at this as being the integral from 0 to 2 of x, okay? And then the integral, I'm bringing x essentially out of the dz and the dy parts of the integral because x is constant with respect to z and y. And then what I have is the integral from 0 to square root of 4 minus x squared. And that's going to be an integral dy. But then when I integrate dz, I'm going to get just z evaluated between x squared plus y squared and 4. Okay, so that's one way to start attacking this integral. So again, I have the integral from 0 to 2 of x, and then the integral from 0 to square root of 4 minus x squared. I'm going to evaluate the z, so I'm going to get z is going to go 4 minus x squared minus y squared. And I want to integrate that now dy dx. Well, I'm going to integrate from 0 to 2. Now I want to integrate dy, so I'm going to get the 4 minus x squared is a constant, so I'm going to get 4 minus x squared y minus 1/3 y cubed, and that's going to get evaluated between 0 and square root of 4 minus x squared. When I'm done, I'm going to have to integrate that dx. So this becomes the integral from 0 to 2. And then 4 minus x squared times square root of 4 minus x squared. So that's going to be 4 minus x squared to the 3/2 minus 1/3. And then I'm going to insert square root of 4 minus x squared. So that becomes, in fact, 4 minus x squared to the 3/2. And I want to integrate that dx. And I still have an x here. So let's make sure that I don't forget that I still had an x there. So if you're following along, make sure that you still have an x there. Okay, so I'm going to get the integral from 0 to 2 of x times, and then I've got a whole 4 minus x squared to the 3/2 minus 1/3 4 minus x squared to the 3/2. So in fact, that's going to be 2/3 x 4 minus x squared to the 3/2 dx. Okay, so one more integral to go. I'm going to let u be 4 minus x squared. And then I'm going to have du be a negative 2x dx. So when I substitute in, I'm going to have an integral. 4 minus 0 squared is 4. 4 minus 2 squared is 0. And I'm going to integrate 1/3 u to the 3/2 du with a negative sign. So essentially, I'm going to replace the 2x dx with du right there, or at least with negative du. This is usually easier if I switch the limits of integration. So this is the integral from 0 to 4 of 1/3 times u to the 3/2 du. And this then becomes integrating u to the 3/2. That's going to be 2/15 u to the 5/2 evaluated between 0 and 4. So finishing up, I'm going to get 2/15 times 4 to the 5/2, which is in fact 64/15. And that is the integral of x dv over the region T. And as you can see, that was a quite difficult integral to do because I was describing this very circular region in the xy plane using rectangular coordinates. So what I would like to do is I would like to take a moment and do one substitution that I could have done, say, earlier in the process of computing this integral, and see if we can make this integral just a little bit easier. So I want to go back to this step and I want to see if I can make a change of coordinates. So here I want to see if I had changed coordinates, whether this part of the integral would have been easier. Okay, so here I'm trying to do this integral, and I'm going to notice that it's over a very circular region, this circular region right here. Okay, it's a quarter circle, and so that quarter circle can be easily described in polar coordinates. Okay, it's an integral that goes from a radius of 0 to 2, and then another integral of theta going from 0 to pi over 2. So I'm going to describe that circular region, okay, by going from 0 to 2 in r and 0 to pi over 2 in theta. So now what am I going to integrate? Well, x is equal to r cosine theta, and then I have 4 minus x squared minus y squared. That's 4 minus r squared. And then dy dx becomes r dr d theta when I make a change to polar coordinates. Okay, let's kind of follow this out and see where this ends up for us. Okay, so I'll notice that I essentially have a function of r times a function of theta. So I can rewrite this as the integral from 0 to pi over 2 of just cosine theta d theta times the integral from 0 to 2 of, let's see, we're going to do 4r squared minus r to the 4th dr. Okay, so doing those two integrals, I'm going to get sine theta evaluated between 0 and pi over 2 times 4/3 r cubed minus 1/5 r to the 5th, and then we're going to evaluate that between 0 and 2. Okay, so sine of pi over 2 is 1 and sine of 0 is 0. So I just get 1 times, okay, so I'm going to get 4 times 2 cubed. So that's 4 times 8 or 32/3. And then I'm going to subtract 2 to the 5th is 32/5. And then of course subtract 0. And it turns out that if you do this, finding common denominator, you will in fact get 64/15. And so I get the exact same value for the integral if I change the polar coordinates. And the integral was just a little bit easier. It didn't have these nasty square roots in it that the previous one did. Here, I don't have to do a u substitution. And so if you start to see that circular region, you know, midway through your computation after you've done the z part of the integral, you could possibly make a change to polar coordinates.